The upcoming videos are going to be about electricity and magnetism. There are many parallels between gravitational forces and electric forces. So we're going to start there with gravitational forces. If you're studying electric forces, then you probably already studied gravitational ones. If not, you can go back to my Physics 1 playlists and review what gravitational forces are all about. I'll give a brief overview here. Gravity is the phenomenon that objects of mass are pulled toward other objects of mass. It's an attractive force. For example, an average 60-kilogram person near Earth's surface would be pulled upon by a gravitational force of about 600 newtons, and it's going to be directed downward toward the center of Earth. Let's draw a force diagram for a person when they're at the peak of a jump near Earth's surface. We'll start the diagram with the tail of the vector being at the person's center of mass, and then we'll just draw a downward arrow, and we'll label it Fg for gravitational force, and we could say how big it is as well. In physics, we use gravitational force vectors to represent the magnitude and direction of the pull that an object feels. And if you check out the diagram in the lower right, you'll see several point masses surrounding an object presumably of large mass. The diagram in the lower right is supposed to represent a large sphere of mass, such as a planet, and several point masses around it. Because all of those objects have mass, they'll all feel pulled toward the center of that massive sphere. They would of course be pulled a little bit toward each other, but we'll treat that as negligible right now. Each gravitational force vector includes a length which is proportional to the strength of the pull, and the direction tells us which way the object is being pulled. Now there could be a few cases where an object wouldn't feel any gravitational force due to this sphere. What would these exceptions be? Think about that for a moment, and I'll give my answers. Well, I would say if the mass were zero, then it wouldn't feel a gravitational force. And we have two formulas that we often use for gravitational forces. One of them is Fg equals mg. And clearly here, if the m were 0, then the force would be 2. We have another formula, though, for gravitational force. This one's used more often for outer space. This is Newton's law of universal gravitation. And clearly here, if the mass were 0 as well, then the gravitational force would be 2. There's one other way, though, that masses won't feel any gravitational force, and that's if the r distance from the object exerting the force were infinity. If we make that denominator infinitely big, then the gravitational force also becomes 0. So that would be a mass which is way out there as r goes toward infinity. The gravitational force becomes 0. So objects in the space around the sphere are said to be in the gravitational field of that sphere. To represent that idea, we can draw vectors showing the direction and strength of the gravitational force that would be applied to a kilogram mass if one were present in the field. In order to draw the field, you don't even have to have mass in that space. You can just draw the arrows regardless, showing how the mass would be pulled if it were there. So that's what these drawings are at the bottom here. These are gravitational field drawings. Now it can be measured that the gravitational field strength near Earth's surface is approximately 9.8 newtons per kilogram. And when we write that in vector form, we write negative 9.8 r hat. Now interestingly, r hat points away from the center of our sphere of mass. This is an example of an r hat vector. So if we do negative r hat, all that means is we reverse the direction. It shows that the gravitational field points in toward the center of mass. And that is the way that massive objects will be pulled, if they're in the field. Now it was Sir Isaac Newton who investigated the strength of the pull around objects of mass. And he discovered how strong the field would be at different points in space. So think back to Newton's law of universal gravitation, if you had studied it before, and decide which of these drawings is actually correct according to what Newton had said. The hint is that this was his mathematical law governing gravitational forces in fields. According to Newton's findings, the correct answer here would be C. As we move away from a sphere of mass, the gravitational field actually decreases. And it gets down to 0 if we were to go all the way out to infinity. It'll be strongest near the Earth's surface. Here's a summary of Newton's law of universal gravitation. In the law, m1 is an object exerting a force, and m2 can be an object feeling that force. But of course, according to Newton's third law, both of these objects are feeling forces at the same time by the symmetry of the situation. So the law tells us the strength of the pull that exists between any two masses. However, Newton admitted he did not know why the phenomenon of gravity should exist at all. It wasn't until Einstein's theory of general relativity that the reason for gravity being there was explained, and that was in the early 1900s. G is the gravitational constant, which tells us how well the gravitational force is transmitted through space. Some other common constants we use with Newton's law will be the radius of Earth and the mass of Earth. We do a lot of calculations with that. And also, we can transform Newton's law into a rule for gravitational field. But when we write the law for gravitational field, we leave out the second mass. All we do is we show the mass who's exerting the field, and we use the gravitational constant as well as the distance from that object. So for example, if I were to draw the Earth here and say I want to evaluate the field at this point in space, then the things I need to know will be the distance to the center here, that'll be r. I'll also need to know the gravitational field constant. I'll also need to know the gravitational constant as well as the mass of that object exerting the field. Let's do an example. I'll use Newton's law of universal gravitation to calculate the force of gravity that acts on a 60 kilogram person who's near Earth's surface. First, I'll start with Newton's law. I'll modify it to include Earth's mass as the object exerting the field. I'll multiply that by the mass of the person who's feeling the field. And then we'll divide by the distance between the person and Earth's center. We'll square that. as a drawing, it could look something like this. All right, so our radius of Earth was given above. It's 6.37 times 10 to the 6 meters. We know the gravitational constant is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. We'll see that the kilograms squared will cancel with our two masses here, and our meters squared will cancel with the radius. Our mass of Earth is 5.97 times 10 to the 24 kilograms. The mass of the person is 60 kilograms. And now we'll divide by our radius. I want to show how to enter a calculation like this into a scientific or graphing calculator. So one of the buttons that turns out to be really useful here is the EE button. So let me start typing 6.67. Instead of writing times 10 to a power, this is not the ideal way to enter something like this. What I'm going to do instead is I'm going to write 6.67. I'll hit second and then EE. The E means times 10 to a power. And then you just put in the power that you want. That's the most ideal way to enter this, because it's going to treat that quantity as just one number. Whereas the times 10 with a caret, it will not do that, and it'll mess up your calculations. So yeah, let's do it like this. We'll do times 5.97 E24. Then we'll do times 60. We'll divide by 6.37 e to the 6. And then we don't even need parentheses here. We can just square that. And it won't just square the 6, actually. It's going to treat the whole denominator quantity as one number. It'll square the whole thing, which is great. Now we're looking for something around 600 newtons. Okay, that's good. 589 newtons. Keep in mind, we could have approached this a different way. We could have used the formula Fg equals mg. Because we do know the gravitational field strength near Earth's surface, right? So we could have done 60 kilograms times our 9.8 newtons per kilogram. And that also comes out to 588 newtons. So just two different ways of calculating a gravitational force. We want to keep this in mind for going forward because the way we calculate electric forces bears a lot of similarity to the way that we calculate gravitational ones.